Today we're going to talk about reverse transcription and integration, and we're going to talk about a couple of very different viruses that utilize this pathway. And I want to emphasize, well, the two viruses, retroviruses and hepatitis B viruses, all right? So those two viruses have very different genomes, as you will see. They both have reverse transcriptase, but not both of them integrate. Only the retroviruses integrate their genome into the host cell. It's a really important difference I want you to remember. There are a couple of main differences between these two virus families I want you to remember. Retroviruses and hepatitis B viruses, those are the main viruses we're going to talk about. A few others scattered in at the end. These viruses probably had common precursors during evolution, and I hope to point that out in their life cycles today. So this is a really interesting way of expressing genetic information, as you will see. First, let's go back to when these viruses were discovered. The retroviruses first. Chicken leukemia virus, 1908. So this is way at the beginning of virology history. Remember, it wasn't until just at the end of the 1800s that viruses were discovered. So this was pretty early on. Bang and Ellerman found a virus, a filtrable agent, which was a virus that caused leukemia in chickens. And then a couple of years later, Peyton Rouse, right here in New York City at the Rockefeller Institute, as it was called back then, discovered Rouse sarcoma virus. And he got the Nobel Prize 55 years later, the longest incubation period for any Nobel Prize. He was a very patient man. These viruses ended up being called tumor viruses because that's what they did. They caused tumors. Even though at the time people didn't look at leukemia as a tumor, eventually we realized that that's what it was. Tumor viruses. Eventually, they were found to have RNA genomes. This took a while because you remember that we weren't cognizant of RNA as genetic material until the 50s. It really was first discovered with tobacco mosaic virus, RNA genome. So then the question was, how do these viruses transform cells? Now, we have a separate lecture on transformation and what that is, and that's really interesting in its own right. Suffice it to say, for today's discussion, these RNA tumor viruses were found to transform cells. That is, if you infected cells in culture, you transform their properties, their morphology, their growth rates, many other aspects of their biology. So it was called transformation. The fact that these had an RNA genome was very puzzling. How could something with an RNA genome transform cells? Because you have to modify the cell permanently, which means you probably do something to the DNA. You put a piece of DNA in or something like that. So it didn't make a lot of sense. So people studied these for a long time to try and figure out how that worked. In 1970, the major discovery, which opened up this entire field, by Howard Temen and David Baltimore, working independently but with knowledge of each other, they discovered an enzyme in the virions of RNA tumor viruses. So this is a particle-associated enzyme, which they called reverse transcriptase. And 5 years later, they got the Nobel Prize. Probably Peyton Rouse was really annoyed at this, that they got it so quickly and he had to wait for 55 years, but they all knew each other. So reverse transcriptase is the enzyme that countered the central dogma, which of course back in the 50s and 60s was that you had DNA in organisms and they went to RNA and then to protein. That was the flow of genetic information. And the whole retrovirus family, so up until 1970, they weren't called retroviruses, they were RNA tumor viruses. They got their name because of this enzyme, and the enzyme was called reverse transcriptase because it reversed the flow of genetic information. So instead of going from DNA to RNA, it went from RNA back to DNA, and then, as you'll see, to RNA and then to protein. So this was a really interesting enzyme. So now we can finally fill in this Baltimore scheme. We've mentioned this group of viruses for a long time, and this is what we're going to talk about today, the retroviruses, which have a plus-stranded single-stranded RNA genome, just like many other viruses, but they do not go through a negative strand RNA intermediate. They go through a negative strand DNA and eventually a double-stranded DNA to get to mRNA. So we'll spend a lot of time talking about this group of viruses. We're also going to talk about hepatitis B virus because it turns out that even though these viruses have a DNA genome, they have a reverse transcriptase. Who would have guessed that? So we'll see where that plays in. All right, back to retroviruses. Baltimore and Temen. Here's Howard Temen, University of Wisconsin-Madison. He spent his career there and did this amazing discovery. These are the abstracts of the two papers that came out in the same issue of Nature. Here's Howard Temen. This is David Baltimore. He likes to fish. This is a big fish he caught here somewhere in New York Bay, I think. So here are the two abstracts. And we interviewed, actually, David Baltimore on TWIV 100, so that's a pretty interesting episode. We also talked about reverse transcription in another episode. So this is very good here. Infection of sensitive cells by RNA sarcoma viruses, those are the RNA tumor viruses that we're talking about, requires the synthesis of new DNA different from that synthesized during the S phase of the cell cycle. He goes on to say that production of the virus is sensitive to actinomycin D. So this is a drug that prevents transcription, prevents going from DNA to RNA. So that was important because these viruses have RNA genomes. And here, these are the basic observations essential to the DNA provirus hypothesis. Replication of these tumor viruses takes place through DNA intermediate. So Temen's idea was that these viruses must have a DNA intermediate. How else could they transform cells? And he thought that the DNA intermediate probably got integrated into the genome, and that's what transformed them. And Baltimore came from more or less the same data. He talked about actinomycin D inhibiting virus production. And these two papers basically report on this enzyme, RNA-dependent DNA polymerase, both same name, in virions, and they worked with two different tumor viruses. Temen worked with Rouse sarcoma virus, which is with the one that Peyton Rouse had identified, and Baltimore worked with a different strain. And you can see they both show that they're in the virions. So this is very important. This enzyme was found in the virions, and that's one of the reasons why they were able to find it easily, because they just purified virus particles and then did an enzyme assay with them. So you didn't have to purify it from infected cells. Now, Temen had a particular insight here that he said the DNA was integrated into the host, and that's what transformed the host. Okay, so we're trying to explain how cells become transformed by an RNA tumor virus. And again, you will hear more about transformation later on. But he said the DNA of the virus was integrated into the host. It's made by this enzyme, became a permanent part of host DNA. And he called this a provirus. So the provirus is the viral DNA integrated into the host cell DNA. That's an important word to remember. We're going to use this over and over again today and in many other lectures. So the enzyme they discovered carried this out. Now, this whole idea of a viral genome integrating into the host, this wasn't new. The phage people had known about this for a long time. So those who had studied bacteriophages that infect bacteria knew that some of them, in fact, integrated their DNA into the host to form what they called lysogens. And here is a picture of bacteriophage lambda, which was one of the earlier models for genetic analysis of viruses. It's one of the tailed phages with a icosahedral head. It has a double-stranded DNA genome. So this is not a retrovirus, it's a DNA virus. The DNA is linear inside the head, and when it's injected into the host, it circularizes and it can replicate, and in some cases it will integrate into a very specific site in the bacterial genome. So this is the bacterial genome shown here in blue. There's a very specific integration site. The lambda genome integrates into it and becomes a lysogen or a prophage within the E. coli genome. And under certain conditions, these bacteria can replicate just fine with this prophage in them. Another condition, it excises. So that's where it's very different, as you're going to see. As far as we know, retroviral genomes never excise from the host. They always stay stuck within there. Okay? And that is important. if we could excise retroviral genomes from the host cell, we could cure HIV-infected individuals, but we can't. We can't figure out how to do that. It happens very easily with phages, but it doesn't happen with retroviruses. So Temen basically took his inspiration from phage. He said, the phage can modify the host, maybe my retroviruses do as well.